everybody. Myself Samir Mondal, a Prime Minister Research Fellow in the discipline of mathematics at IIT Madras. Today we'll discuss about partial derivative of multivariate calculus. Basically here we'll fix about two variable functions. Okay. So in my previous lecture we already discussed about limit and continuity of multivariate function. Okay. Today we are going to discuss about partial derivative of multivariate function. Basically we are restricted ourselves for second variable only. Okay, two variable functions. Okay, first please someone tell me what do we mean by derivative of a single variable functions, at least geometrical interpretation of derivative of a single variable function. Please tell someone. Please tell. Please tell someone. Okay, so geometrical interpretation of derivative. Okay, derivative of a single variable function is like that. Suppose this is your coordinate plane. Okay, and suppose this is your functions f of x. Okay, so what do you mean by derivative of a function at the point, some point take a. Okay, this is your x equal to a at the point. So derivative of a single variable function at the point, at the some point, is nothing but a slope of that tangent. Okay, this is your tangent. The slope of the tangent at a point, at a given point, is derivative of a single variable functions. So can we generalize this concept for multivariate functions? Basically here we are looking for only two variable functions. Okay, suppose I am giving giving you one two variable function f of x y, where x and y are independent variable. Okay, so could you please tell me what is the partial derivative of these functions at a given point a b? Here our f is from D, a domain is subset of R to R, real valued functions. Okay, so could you please someone tell me what do you mean the partial derivative of this function at a point, a given point, suppose AB, take AB. Okay, which is given D. Okay, please someone try. Okay, so before going to the definition of partial derivative, I want to tell one observations. Okay, suppose this is your function of two variable. Okay, f of xy is a function of two variable. If you fix one variable, okay, take y equal to b and fixed it, plug it here, so what we will get? We will get x b. Right now this function will treated as your one variable functions. Okay, after plugging y equal to b this point. Okay, now we can think the same concept as like our derivative of a single variable functions. We can generalize same things for your two variable functions after plugging one particular variable. Okay, so what do we mean by partial derivative? Okay, so as is geometrically one can think like that. Suppose this is your partial derivative. Okay, geometrical interpretation of partial derivatives. First I am telling like this one, then we will go for general definition. Okay, partial derivative. Okay, this is x, this is your y coordinate, this is your z axis, x axis, y axis, z axis. Okay, take this is on surface, this is your one surface. Okay, z equal to f of xy. Okay, your this is your given functions. We are looking for finding the partial derivative of this function at the point AB. Okay, which is in your the domain D. Okay, so what we can do, we can here after plugging y equal to b, we get that this is a one variable function. So we will do same thing. This is your surface. Okay, so if you take this plane y equal to b, okay, if you take this plane, what will get? Like that. Okay, we will get this plane. So we will get this plane. This is your y equal to b plane. Okay, this is your y equal to b plane, this is your y equal to b plane, this one. Okay, and this is your surface. So we are looking for intersection between surface and this plane. So we will get one this curve only. Okay, so this is your nothing but a intersection of z equal to f of xy. Okay, intersection of surface of this one and the plane y equal to b. Okay, so this is your that one, intersection of this one and intersection of this plane. Okay, so now after plugging one variable, we will get single variable functions. So right now we can think this one as a single variable function. So partial derivative at a point AB. Okay, this is your AB. Okay, so what this point is, this point is A, B, f of AB. Okay, so your tangent, draw a tangent here. Okay, like that, this is your tangent. So partial derivative of a function, two-variable function f of xy at a point AB is nothing but a slope of the tangent at intersection of this one and intersection of this one and the plane y equal to b. Okay, it's fine, Amardeep. So we can write like that. Okay, let f of xy be a real valued function defined on a region D, which is subset of R2. Let A be one given point in D. Okay, the partial derivative of f of xy with respect to x at the point AB is f of xa, AB equal to del f del x at the point AB. Previously what I told, that fix the one variable. Okay, this is after plugging y equal to b, we get one single variable functions. Take the derivative with respect to x. After that put x equal to a. So this is your partial derivative of f of x with respect to x at the point AB. This is geometrically, you can tell the slope of this tangent at the point, this one AB, f of AB. Okay, at the point this one. This is not clear now. At the point this one on the function or on the curve is the nothing but intersection of j equal to f of x and the plane y equal to b. Okay, is it fine? Now we can define this one as a, because after plugging here, okay, after plugging y equal to b, we got one variable function. Right now we can think, or we can use our known definition. Okay, this is nothing but equal to h tends to 0 f of a plus h comma b minus f of ab divided by h, provided this limit exists. Okay, it's fine. This is our definition of partial derivative at the point AB. Okay, one can note that f of xb must be continuous at the point x equal to a. Okay, one can prove easily this one. Okay, I am skipping this proof. Okay, similarly one can define the partial derivative of the function f of xy, okay, with respect to y at the point AB. Okay, that is defined by is f of y at the point AB is nothing but partial derivative with respect to y at the point AB. Here when we are taking the partial derivative with respect to y, we have to plug the one variable x variable. Okay, we have to plug x equal to a, then we have to take the derivative of that function. So we are plugging x equal to a. After that we are getting this function. Take the derivative of this function at the point y equal to b and use our known definition. Okay, then we will get limit x tends to 0 f of a b plus k minus f of ab divided by k. Okay, provided this limit exists. Okay, here also one can note that after plugging, okay, when you are plugging x equal to a, we are getting these functions. Okay, this function, if partial derivative exists, means this limit, if this limit exists, f of ay must be continuous. Okay, it's fine. So I want to recall once time the geometric interpretation of partial derivative. Okay, so this is your given functions. Okay, this is your given function z equal to f of xy. Okay, so we want to plug one variable, okay, or one quadrant, whatever you tell. So when we want to plug one variable, take y equal to b. Okay, so in 3D it is a nothing but a plane. So this is f of xy, this is your one function of two variable. The intersection between this one, this function, this surface, and the y equal to b plane will get one curve. Take this is name as c. So this one is c. Okay, so we are getting c our intersection of f of xy and the plane y equal to b. So partial derivative at the point ab with respect to x. Okay, when we are doing the partial derivative with respect to x, then we have to plug the another variable. Okay, so intersection of the plane f of xy and the intersection of the function f of xy and the plane y equal to b, we are getting one curve c here. Okay, this is your one curve. So we are looking for partial derivative of the function f of xy at the point ab with respect to x. It is the slope of the tangent at this point, on which curve? On the curve c. Okay, to the curve c. Okay, this is your geometrical interpretation of partial derivative with respect to x. So here I am writing this one, geometrical interpretation. Okay, geometrical interpretation. Okay, let f of xy be a real valued function. Okay, on a region D subset of R2. Okay, and also given that AB belongs to your domain D. Okay, if C is the curve of intersection, okay, C is the curve of intersection of the surface z equal to f of xy with the plane y equal to b. Okay, then the slope of the tangent line, okay, to C. C is the intersection of the surface z equal to f of x and the plane y equal to b. Okay, so we are getting C after plugging one variable. Okay, when we are trying to do partial derivative with respect to x, then we have to plug the other variable y. Okay, so we are get this C is nothing but a one single variable function. Okay, so then the slope of the tangent line to C at the point a b f of a comma b is the partial derivative of f of xy with respect to x at AB. Okay, it's fine. Now we'll go for few example. Okay, so try to find this example. Here we have defined two definition. One definition is limiting sense, this one. Okay, another definition we will plug one variable, and after that we will do differentiate with respect to, suppose here we are, okay, this will be, sorry, this will be y. So here we are trying to do we need the partial derivative with respect to y. So here we plug the x equal to a variable. Okay, here plug x equal to a, then we get one variable function, then we did that derivative of that function with respect to y. Okay, so after that we will put y equal to b value. Okay, same things here we will do. Okay, this is your one function is given, if xy equal to given is 4 minus x square minus 2y square. You have to find f of x with this means you have to find the partial derivative with respect to s at the point 1 1. You have to find this one. Okay, so we'll see the two approach. One is limiting approach and one is we'll plug here we have to do partial derivative with respect to x, so we'll plug the y equal to something. Okay, something in here say 1, so we'll plug the one y variable, then we'll do the differential with respect to x, then we'll put the x equal to 1 value. We'll do these two process. Okay, first we'll do limiting process. Okay, f of x y is nothing but your limit s tends to 0. Okay, f of 1 plus h 1 minus 1 1 divided by, this is the definition of partial derivative with respect to 1, this one. Okay, here our a equal to 1 and b equal to 1. Okay, so put the value here. Okay, here so we are getting limit h tends to 0. What is the value of f of 1 plus h comma 1? You have to put. Okay, this one 4 minus 1 plus h square minus 2, 1 square means 1. Okay, so minus f of 1 is 4 minus 1 minus 2 divided by h. So what we are getting, limit s tends to 0, we are getting here 2 minus 2h. So we are here getting minus 2, here we are getting minus 2 minus 1, sorry, plus 2 minus 1 minus 1, here we get minus 1, so 0. Okay, and what we are getting, minus h square minus 2h divided by h, so ultimately we are getting minus 2. This is the one approach, this is the limiting approach. Okay, so we try to find this one in different approach. Okay, so here we have to find the partial derivative with respect to x, so we have to plug one variable, put y equal to 1 in the function. So what we will get, we will get 4 minus x square minus 2. So do take the derivative with respect to x. Okay, what we will get, minus 2x, put the value, so this is minus 2. Okay, it's fine. This is the another approach. Now I am giving one exercise. Okay, try to solve this one. You have to find the plane this one given, plane x equal to 1 intersects the surface z equal to x square plus y square in a parabola. So what is the intersection of this one and this one? We will get one parabola. This one is x1 equal to y, x equal to y is this one is one plane, and this one is your another surface. So after intersecting both two, we will get one parabola. Okay. So you have to find the slope of the tangent to the parabola at the point 1 to 5. So please tell me what they are asking. So what we are, this is the parabola is the intersection of this surface, okay, z equal to x square plus 1 and the plane x equal to 1 plane. So we are getting one parabola. So you have to find the slope of the tangent to the parabola at the point 1, 2, 5. So they are asking the partial derivative of the function z equal to x square plus y square, okay, with respect to y. Here we are plugging x equal to 1, okay. So this parabola is nothing but the intersection of this function z equal to x square plus y square and x equal to y plane. So they are asking the partial derivative of the function z with respect to y at the point this one. So this is very simple, no? So this is given, okay. So they are asking this one partial derivative. So this is 2y at the point 1, 2, 5, okay. At the point 1, 2, 5, so we will get 4. This is the slope of the tangent to the parabola at the point 1, 2, 5, okay. So now we want to define the partial derivative of second order, okay. For a function f of xy, partial derivatives of second order are, okay. So f of xy, at first we will do the partial derivative with respect to x, then again we will do that partial derivative respect to of that function of this one with respect to x, okay. This is del f del x, so we will get del 2 del f del x square. Similarly we will get for this one is this one, sorry, this should be y, so this is nothing but a this one, okay. Now what do we mean by this one? So here x is first, then is y, so we will do the partial derivative with respect to x first, then we will do partial derivative of that one f of x with respect to y, okay. So at first we will do this one partial derivative with respect to x, then we will get one function, then again we will do partial derivative of that function with respect to y, okay. So y will do last, okay. Del f del y del x, okay. Similarly for this one, at first we will do with respect to y, then we will do with respect to x, so ultimately we will get this one, okay. It's fine. So similarly our higher order partial derivative also we can define. Okay, similarly higher order partial derivative are defined. Okay, for example this one f of x y. So at first what we will do? At first we will do the partial derivative with respect to x then y. Okay, so at first we will do partial derivative with respect to x. Okay, then we will do partial derivative with respect to x again, then we will do partial derivative with respect to y. Means this is del del y, del x, del x. This is okay, nothing but y dx dx. Okay, here one can ask one simple question: is these two derivations are same? F of xy and f of yx. This is my question. So is these two derivations are same? Equal to f of yx. Is this one correct? This is my question. Someone can try it. Okay, how these two quantity are same? You can on your mic and you can talk. Yeah, you can on your mic. I am giving one example. Try to find f of xx and f of yy. Okay, this is your function f of xy is xy into x square minus y square divided by x square plus y square. Okay, when your xy is non-zero and at the point 0 0 is defined as 0. Okay, so here you have to find these two quantity. Okay, at the point 0 0. Okay, you have to find f of xy at the point 0 0 and f of yx at the point 0 0. Okay, so what is this quantity? F of xy at the point 0 0. So here at first we will do the partial derivative with respect to x, then we will do again partial derivative with respect to y. Okay, so means y second means we will do the partial derivative with respect to y at the last. So what will be the limit definition? Limit k tends to 0, f of x 0k minus f of x at the point 0 0 divided by k. Okay, so we need this quantity, this quantity, then we can tell what is the value of this one. So we have to find this one. Okay, f of x's at the point 0 0. What we will get for this one? You can check it. We will get this one 0, And what we'll get for this one? F of x 0 comma k, this is nothing but, sorry, yeah, so limit h tends to 0, f of h comma k minus 0 comma k divided by your h. This is the limit definition of partial derivative with respect to x at the point 0 comma k. Okay, so limit h tends to 0. What is your f of hk? F of hk is this full quantity. Okay, okay, this full quantity. Okay, full quantity. So put the value here, h k h square minus k square divided by your h square plus k square, here is 0. Okay, divide by your h, so this will be cancel out. Okay, so ultimately what we will get? Ultimately we will get minus k. Okay, so this quantity we are getting minus k, this quantity, this quantity minus k, this quantity is your 0. Okay, limit k tends to 0 minus k 0 by k, so here we are getting minus 1. Okay, for this one what we are getting? We are getting minus 1. Okay, and for another one, for f of yx at the point 0 0, so what is the definition of this one? Is limit h tends to 0. Okay, here already f of yx means we already did the partial derivative with respect to y first, then we will go for x. Okay, so f of partial derivative with respect to y at the point h comma 0 minus f of y. So again you have to find these two quantity, this quantity, this quantity. You can check easily, this one is 0, and for this one you have to find. Okay, k tends to 0. Okay, f of hk minus f of h comma 0 divided by h, sorry, this should be k, no? Yes, so this quantity what we will get? Okay, 1 minute. F of y, okay, it's fine. Okay, so ultimately we'll get h k, okay, h square minus k square divided by h square plus k square divided by k, and this is 0. So your k will be cancel out. Okay, so what we'll get? We'll get only h here. Okay, so ultimately what we'll get? We'll get limit h tends to 0, h minus 0 by 0 equal to 1. Okay, so we are getting f of xy at the point 0 0 is minus 1, f of yx at the point 0 0 is 1. Okay, so these two quantity are not same. From here we can conclude that these two quantity are not same. So what is the lack here? For the reason is these two quantity are not matching. So one can observe here that this quantity, okay, the partial derivative of the function f with respect to x, if you check this function, this function is not continuous, because on this curve, on the curve 0k, okay, when is k is vary and your first coordinate is fixed, on this path we are getting that limit is minus k, okay, but if you look for another one, f of x h comma 0 or something 0 0, we will get directly 0, okay. So on to different path we are getting to different limit. So the quantity f of x, similarly we can prove that the quantity f of y not are continuous functions. So this is one lack, okay. So under some condition on those two quantity, f of x, f of y and f of xy, will get the this required result. This theorem is known as Caillard theorem, okay. Caillard theorem, what it says that let D be a region in R2, okay. Let the function f from D to R have continuous, okay. So this function have continuous first and second order partial derivative, okay, derivative on D, them your these two quantity are same, okay. Is fine? Please tell me. Is it fine? So do you have any question? Please tell me right now if you have any question. If you don't have any question, I am going for one observations. Okay, so initially we have seen that partial derivative with respect to x at the point AB is nothing but, okay, we'll plug one. When we are going for partial derivative with respect to x, we will plug y, so we will get this function f of xb. So when look for partial derivative of the function f at with respect to x, we will do the differentiate, okay, with respect to x, then we will put that x equal to a, then we will get this quantity. But if someone observe, we can observe something. We observe that f of xp is not same as limit xy tends to ab f of x, this one, okay. So this quantity and this quantity are not same, but it seems to be same, but truly speaking it's not same. I am giving one example, okay. To see this, let f of xy, one function is given by 1 if your x is greater than 0, 0 if your x is less equal to 0, Okay, means your function is like that. Okay, one little bit gap is there because your when your x greater than 0, x will be 1, otherwise this is 0 up to here. Okay, this is your given function. Okay, so you have to find this quantity f of x at the point AB. Here we will look for this one 0 0, f of x at the point 0 0. What will get this quantity? One can observe that this is 0 for all x if x is greater than 0. When x is your greater than 0, okay, so we will get the partial derivative with respect to x at the point 0 0 is equal to 0. Okay, and similarly also we can write this one. Okay, 0 for all x is greater than 0 is also 0 when or for all x is strictly less 0. At the point 0 also it's 0. Okay, okay, so here we can observe that if your limit xy tends to 0 0, f of xy is nothing but a 0, but one can observe this one f of x at the point 0 0 does not exist. Okay, so how we can observe this one? What is your reason? Is limit h tends to 0, f of h comma 0 minus f of 0 0 divided by 0. This is your known formula. Okay, so what is this quantity? This quantity will be either 1 or 0 divided by 0. So this quantity does not exist. Okay, it's fine. So here we have seen that this quantity does not exist, but this limit is 0. Okay, so one question arises, when these two quantity, this quantity and this quantity will be equal. Here one can observe, here what we can observe, this function f of x, okay, after taking the first derivative, this function is not continuous at the point 0 0. For the reason we are getting this lag. Okay, so one note is like that. What is the note? So here this example that these two quantity are not equal. Okay, so when this quantity will be equal, if f of xy is continuous, okay, at the point AB, then these two quantity are equal. Okay, so if you have any question, them you can do, otherwise I will stop here. Okay, so in my next class we will discuss about increment theorem, total derivative and partial derivatives. Okay. Okay then, see you. Bye bye.